Let's look at the fourth and final factor that we will evaluate when we're ranking a series of acids or bases according to strength, and that's hybridization effects. If we compare ethane in blue to ethene in green, we see that the pKa values of the protons on the carbons there are different, even though we have hydrogens connected to the same atom, so it can't have a different elemental effect. There's no resonance that can take place, and there's no real inductive effect going on here. For some reason, the pKa values for the two different protons are different. And so let's take a look at what's going on. When we want to make a comparison of two acids in terms of strength, what we really need to compare are their conjugate bases, as we've seen over and over again in the past few videos. And so if we compare the conjugate base of ethane in blue to the conjugate base of ethene in green, really the only difference is that the carbon left with the negative charge on ethane is sp3 hybridized, where the carbon left with the negative charge in ethene is sp2 hybridized. Recall that the difference between an sp3 hybridized carbon and an sp2 hybridized carbon is the percent in relative S and P characters. So sp3 hybridized carbons are 25% S and 75% P, where sp2 orbitals are composed of 33% S and about 67% P character. Since s orbitals do not have a node at the nucleus like p orbitals do, the higher the percent s character that a given orbital has, the closer the electrons are held to the nucleus. So when we're comparing the conjugate bases of ethane and ethene and taking a look at the sp3 versus sp2 nature of the carbons bearing the negative charge, what we're really comparing is that there's a slight difference in how closely these electrons are being held to the nucleus of the carbon atom. And so they're being pulled in just a little bit stronger to the sp2 hybridized carbon nucleus. And you might recall when we talked about the electronegativity effects a few videos back, that when electrons are being held in closer to the nucleus, that's a stabilizing effect. So it turns out that the sp2 hybridized carbon is more stable with the negative charge than is the sp3 hybridized carbon. So you end up with a more stable conjugate base. Hopefully by now you get the idea that when you have a more stable conjugate base, it means that its parent acid was more acidic. And so this accounts for the differences in pKa between the proton here, which was around 50, versus one of these protons, which was around 44. So let's continue with this trend. When you have something like acetylene, where you have two carbon atoms connected through a triple bond, and there's a proton on one of those carbons, the pKa drops all the way to 25. Recall that a carbon atom involved in a triple bond is sp hybridized, meaning that the orbital is composed of 50% s and 50% p orbital. Since a deprotonated acetylene leaves the negative charge on an sp hybridized carbon, this is even more stable than a negative charge on an sp2 or sp3 hybridized carbon. So the pKa of a proton on an sp carbon drops dramatically. The bottom line is that when an atom has higher percent S character, the protons on that atom are going to be more acidic. So to recap, protons on an sp3 hybridized carbon have pKa's in the 50 range. Protons on an sp2 hybridized carbons have pKa's in the 38 range, and protons on an sp hybridized carbon have pKa's in the 25 range.